In this video, we're going to go over merge sort source code. This is relatively, well, simple, should I say. And you'll see why in a minute. So I know it's not a lot of code, just hang on for 1 second. All right, so we have kind of our base sorting function or method, right? So this is the one we've been using for all of our algorithms. So we have sort, takes in a comparable array, so we can sort anything that's comparable. We have here basically the creation of an auxiliary array. And this is something we'll need later on. Basically what happens is, right, is that if I have some input, right, my input looks like this, I'll need to create an auxiliary array, right, that's the same size and has space potentially for every element in the original array. What this will be used for is when we're doing that merge step, because we need to basically have a place that we can move our elements to merge to, right, so it's like we have a backup store, we want to move everything that we want to merge there, and then take them and move them back to the proper array in the order they actually belong in. Because of that, because we have to do that merge step where we are basically combining things together, we need to have a holding place or a temporary location where I can put those elements until they've been sorted. So we do need to have an auxiliary array. This is maybe one of the, so this is a performance issue, right? Well, I shouldn't say issue, but it's a performance concern. But it doesn't really show up in the big O, right? Big O is n log n. This is something a little bit different. This is basically saying that we use more memory, which is something we haven't really talked about, but is another consideration. Not just how much CPU time does the algorithm take, but how much memory does it take. All right. So, jumping back to the source code, we have a call a sort. So sort is going to be our merge sort. So this is the algorithm, the whole algorithm, if you would. It takes a bunch of parameters, right? So it takes 4 parameters. It takes A, which is the data I want to sort, aux, the new array I just created, and then 2 integers, 0, and in this case it'll end up being A.length minus 1. Those are my bounds to say I want to sort this array from index 0 to the very end. So arrays are base index 0 or index 0 based, right? So we have to go basically one less than their length to get to the last index in them. So this is basically giving me, this space over here and this space over here is what those 2 parameters are going to look like. So this is equivalent to me saying merge sort, please sort the entire array, right? That's the equivalent of what this line is saying. All right, and then of course, right, it'll jump down and it'll call this thing over here, and we'll go there in a minute. Last thing in that main sorting function is going to be the assert. And the assert is basically just to make sure that everything went well, right? To make sure that everything ended up being sorted into the position that it's supposed to be in. Pretty much the same as the other sorting algorithms. All right, so take a look at sort. So sort has those 4 parameters, and we already talked about a little bit. So we have A, aux, low, and high. Let's walk through the code a little bit. So first of all, we have this if check. This if check is to check to see whether we're done. So we're done in kind of 2 cases. One case, well, okay. So in general, the case is if I have 1 or fewer elements, then I'm done. Okay, I don't need to sort. Right? If I have no elements, if I have 1 element, I don't need to sort. And so you can see here I have my high less than or equal to low. Basically, what's checking to see is if they end up being like the same, right? Because if they're the same, that means that we're looking at an array of 1 index, right? Because it's like, oh, sort from here to here, but when the here and heres are the same, well, you're just looking at 1 element. Okay, that's what the equal is taking care of. The less than symbol is taking care of the case where sometimes if you run this thing too long, it'll try to go, it'll set, they'll set low to something higher than high because it's like they're flipping, right? It's like you divide, and then you have some numerical errors and you flip your order somehow, and your low isn't your low anymore, it's your high. That's the other thing it's looking for. And basically what that means is you've gone to the end. You try to do division, but you don't have anything left, right? It's basically blank. So either those 2 cases, right? Either you have this blank thing left, right, with the bad indices, or you have the indices that are the same, meaning it's just 1 element. Either case there, we're done, right? We don't need to do any sorting, right? We're done, okay? So this is somehow our base case. That's what I would annotate that as a base case. All right, then I have my mid variable. So what this is doing is picking my midpoint. Okay, so what is the element I want to split on in the middle? So we have this formula here, low plus high minus low divided by 2. This is, basically I'm averaging 2 values, right? Is what I'm doing. I'm getting something right in the middle. One thing though is that this formula maybe is a little more complicated than the way some people would write it. So I have low plus high minus low divided by 2 versus other people, right, might just write this. Okay, so these are kind of 2 options if we're picking the midpoint. Real quick. Ask yourself what might be the benefit of the left one, right, over the right one. So why would we actually do this versus not this one over here? It is a little bit of a numerical issue, right? It's a little bit tricky, but think for 1 second. Why might we want to do the left side versus the right side? The reason in this case is because of integer overflow. So if low and high are both really large integers, when we add them, we're not going to be able to hold that number, right? So we're not going to be able to divide it by 2. That is a little bit of a, it's a numerical issue, right? It's one that hopefully we don't hit, but it exists in this right-hand code. Right, if low and high are really large, we can add. We would try to add them, but we would fail because they give a result that's too large. Left-hand side doesn't have that issue because we know, right, low and high by themselves are already valid numbers. So low is good, high is good. High minus low obviously has to be a valid integer because it's going to be less than high, right? So we know that this thing inside is good. Divide by 2, obviously it's getting smaller, so it's still going to be good. And then we add it with low. So left-hand version basically has no chance of any sort of integer overflow happening, whereas the right side does have a small chance of an issue occurring. All right. So we've basically checked our base case, we've picked our midpoint, right? Our midpoint is basically to say, this is where my split is, right? I decided I need to do that divide operation because that's how algorithm works. This is my point. I'm going to send this left half to go get sorted, and this right half to get sorted, and then I'm going to merge them together. So yeah, that's actually exactly what we do on the next 3 lines. So if you look over here, I have to do a sort, and these arguments in the front are all going to be the same, right? A and aux basically go to everybody. You can see that first sort is going from low to mid, right? The second one is going from mid plus 1 to high. And note that these parameters are all right inclusive, right? So it's like I'm going to sort from low to mid, right? Including both the elements at those 2 indices, at the low index and at the mid index. And then I sort the other side, right? From mid plus 1, right? Step 1 to the very end, right? To high. So I've done my 2 calls here. I've sorted each side, right? These are recursive, right? These are going to be calls that go over, here to the top level sort. Then once I'm done with those where I have my array where I have basically, this stuff is all sorted over here, this stuff is all sorted over here. I got to merge them together. So I make one called the merge. Merge again takes A and aux, and it takes 3 parameters. It takes the low, medium, and high. Well, low, middle, and high. Okay. It's basically saying that I have, this region over here, this region over here, combine them together, right? So I have my midpoint over here, high over here, and low over here. It's saying, I got these 2 things, I got to combine them together. Note that it is assuming that they are back to back. So it's like one little region, combine everything together in that little region. And then so there we have it, right? So that's the entire algorithm, right? So kind of the everything we talked about right in the previous couple of videos, right? All of that is embedded here in these 3 lines of code, right? To make these 2 calls and then do the merge operation. And yeah, that's merge sort. Air quotes here, that's merge sort. This is a hardy algorithm. One thing we're missing here, and we'll have to spend a little bit of time on, is this notion of merge. So merge is going to be a function that I give it 2 ordered inputs and it produces for me one larger ordered input that has both of them combined together, right? That's going to be my essential piece. That's what's missing here. And that's actually what does most of the work, right? I mean, if you look at the code we have on the screen, you'll notice there's nothing like an if statement or a loop or anything. There's nothing that we're typically used to, right? The less comparison, the exchanges, right? There's nothing we're typically used to seeing for sorting different sorting algorithms. Instead, we're just doing a bunch of different calls. All it actually ends up being encapsulated in this merge function, right? So the merge function is kind of the heart of our algorithm, right? It's not technically doing sorting, but it is doing, it's not technically a sorting algorithm, but it is kind of providing the backbone logic, right, for being able to take 2 things, right, and compare them and see what order they go into. So that's going to be the next thing. That's going to be kind of where most of the computational work happens in merge sort.